everyone. Welcome to the M2L31 series Level 1 training course. Today, we'll go over an example program that reads a temperature sensor via Low Power I2C, showing how to automatically acquire temperature data in low power mode using the auto operation mode. You can download the example program from the link in the video description below. Once you've downloaded it, just extract the files and open the project in the Kyle development environment following the provided path. Let's first take a look at the flow of this example program. The M2L31 uses Low Power I2C in auto operation mode, combined with Low Power PDMA and the Low Power timer to periodically read the temperature sensor. The Low Power timer automatically triggers the Low Power I2C every 500 milliseconds. Once the Low Power I2C is started, PDMA channel 0 is activated to send the command data stored in Low Power SRAM to the temperature sensor. Then PDMA channel 1 moves the sensor's response back into Low Power SRAM. When the data transfer is complete, a PDMA interrupt wakes up the CPU to process and calculate the results. The program uses an add-on board called the M2L31 Learning Board, which has I2C interface temperature sensor, which part number is NCT7712Y. The datasheet can be downloaded from the sample code folder. Next, let's use the bus matrix to look at the relationship between the different peripherals. Here, the CPU acts as a master and can read from and write to peripherals in the low power domain. Inside the low power domain, Low Power PDMA is also a master. It can read data from Low Power SRAM and write it directly into Low Power I2C, completing the data transfer without waking up the CPU. Next, let's move on to the code itself and start from the main function, where you can see the overall structure of this example. In this Low Power I2C demo, the key components we use are the Low Power timer, Low Power I2C, and Low Power PDMA. These three modules work together to handle the entire automatic transfer flow. As for the initial system setup, like the minimum current init, system init, and UART init functions, you can refer to the Low Power timer sample code video for detailed explanations. In our previous Low Power I2C video, we mentioned that Low Power I2C has three operation modes: write command, read command, and random read command. Here we're using the random read mode, which is special because the master sends a command first and then reads, using a repeated start between the send and read commands. In the program, the Low Power I2C trigger init function is used to configure the behavior of Low Power I2C in auto operation mode. First, the trigger source is set to Low Power timer 0, and the operation mode is set to 011, which corresponds to random read command with repeat start. Additionally, the RxCNT and TxCNT fields need to be set correctly to specify how many bytes to receive and transmit. Note that both fields should be set to the actual number of bytes, -1. From the temperature sensor datasheet used in this example, we can see why the random read mode is needed. The diagram shows the sensor's waveform. The master first sends a write command with an index to the slave, and then issues a read command. This allows it to read 2 bytes of data at once. In the program, the write command, index, and read command are placed sequentially in a buffer and sent in order. This way, we receive data 1 and data 2, completing the entire read process. The actual waveform shown in the bottom right corner matches this sequence exactly, fully corresponding to the program flow. Next, let's take a look at how Low Power PDMA handles sending commands and receiving data. First, PDMA channel 0 is used to send commands to the sensor. That is, the write command, index, and read command we mentioned earlier. The sensor's response, data 1 and data 2, is then moved by PDMA channel 1 into the destination array stored in low power SRAM. Now you can open the Kyle project file from the path we mentioned earlier. Next, click Build to compile the project. Once the compilation is complete, connect the development board to your PC via the debugger's USB port. Then, click Download to flash the program onto the board. Once the program is successfully flashed, we can open a serial communication tool. Make sure to turn on the TX switch on the development board, as we mentioned earlier. You'll then be able to see the temperature values from the sensor, displayed in the terminal. Next, let's use a current measurement tool to see how much power the system is actually consuming. From the results, we can see that because we don't need to wake up the CPU constantly in this application, the overall average current consumption is only around 30 microamps. This demonstrates just how efficient the system can be when using low power I2C with auto operation mode. By looking at the current waveform in relation to the program's behavior, we can see that the peaks indicate when the CPU is awakened. At these moments, it reads the temperature sensor data and then returns to sleep mode. That wraps up our introduction to the low power I2C sample code in this training session. Thank you for watching, and if you'd like to learn more, please feel free to reach out to us.